All right, we are in section 11.4. We've been doing our limit definition of derivative. We've done a couple different examples where we found the derivative of our functions. The first function was quadratic, it was an x squared. The second function was a cubic, it had an x cubed. Now let's talk about how to find a derivative of a rational function. So look at this function. F of x is equal to 4 over x. And we want to find the derivative. Well, just like before, we can still find the derivative using that limit idea. We can do the limit as h approaches 0 of f of x plus h minus f of x all over h. So let's do that same thing. Wherever we see an x in our function, we're going to plug in an x plus h minus our original function all over h. So I have something that looks like this, right? Okay. The problem is, I don't know if you've seen this before, but I have a triple layer fraction. And there's a numerator and a denominator, but I don't know what that last layer is, right? And so normally, we're not used to triple layer fractions. Sorry, that's my dog. Hey, no. Sorry about that. We're not used to triple layer fractions. And so what we have to do is use some algebra skills to get those triple layers into just two layers, a numerator and a denominator. So I'm going to ignore this bottom layer for a second. Don't let me forget about it. But we still have to take this and divide it by h. So don't let me forget. We're going to pause on that though for a second. If you look now, I have a 4 over x plus h minus 4 over x. I have two fractions that I'm trying to subtract. And hopefully we remember that anytime we're adding or subtracting fractions, we need to make sure that we have a common denominator. And right now these fractions don't have a common denominator. The first fraction has a factor of x plus h. The second fraction just has an x. Everybody needs the same stuff, a common denominator, before we can add these together. So the first fraction needs an x on the top and the bottom to keep my fraction balanced. That means my second fraction already has an x, but it needs an x plus h. Now be careful, you can't just add h to the top and bottom. It doesn't work like that in math. We have to make sure that we multiply by something. So we have to multiply by the whole piece, x plus h, okay? But now both fractions have a denominator that has an x and an x plus h. So I should be able to take these two now and combine them together. So this is what we have. We have a 4x minus, let me write it. We have a 4x minus a 4 times an x plus h on the top. And I'm going to take this negative 4 and distribute it. So that's how I got the red piece that you see in your numerator. We have a 4x minus a 4x minus a 4h all over my common denominator of the x times the x plus h, right? When we add fractions, we add or subtract the numerators, but we keep that common denominator. So now if you look at my problem, the 4x and the negative 4x should cancel each other out. Isn't that what's supposed to happen? Everything without an h should cancel? Okay, but don't let me forget. Remember, there was supposed to be a divided by h on this problem, wasn't there? Remember I told you we were going to pause on that for a second? But I still have two layers, and I don't really want to add another layer and divide by h. So instead of dividing by h, couldn't I multiply by the reciprocal? Isn't that the same thing as dividing? You've talked about that before in previous math classes. So instead of dividing by h, couldn't I multiply by his reciprocal and multiply by 1 over h? What that allows us to do then is put my numerators together and my denominators together. When we multiply fractions, we multiply across the top and we multiply across the bottom. So on the top, I would have a negative 4 and an h. On the bottom, I would have an x, I would have an h, and I would have an x plus h, all being multiplied together. So you can actually write it in any order, but I have an x times an h times an x plus h. So I'm going to write it like that. So you've noticed now, I now only have two layers. I don't have that triple layer fraction anymore that I didn't want. So again, instead of dividing by h, we can multiply by his reciprocal, 1 over h, and then I can have two layers instead of three. Okay, let's keep going. You notice in this blue step, I have an h on the top and an h on the bottom that are both just being multiplied by. So they're factors of that we should be able to reduce. If I reduce an h from the top and an h from the bottom, that leaves me with a negative 4 over x times x plus h. And remember to keep that limit in front because we're still doing the limit as h approaches 0. We want to make sure that we smush these 2 points together and find the instantaneous rate of change, or the derivative. So now that we've simplified, let's try to apply that limit idea and do our direct substitution. If I plug in a 0 there, I have x plus 0, which is just x, and then I have x times x, which is really x squared. So my derivative at any point, my instantaneous rate of change at any point, would be negative 4 over x squared. Whew, that was a good one. Make sure you practice that. I had a little bit of fractions in there, so make sure that you're comfortable getting that common denominator and multiplying by reciprocals so that we can simplify. Okay, so we've seen this idea before, the equation of a line, right? Y equals mx plus b. And we've seen point-slope formula, where as long as we have a point and as long as we have a slope, we should be able to come up with the equation of any line. If we have a point, we can plug in our x and our y. And if we have a slope, we can plug it in there and find our equation of our line. So what this is saying is we can find the equation of any tangent line if we have the slope of the tangent line and a point. Remember, the slope of the tangent line is the same thing as derivative. So if we can find the derivative, then that's our slope, and then we can use the point and then find our equation of our tangent line. Let's do part B in this video so we understand equations of tangent lines. So the first, or part B says find the equation of a tangent line to the graph at x equals 2. So it looks like we're using the same exact function here, the 4 over x. And I'm not sure what that equation looks like, but I do know that there's a tangent line that touches it once, and we want to figure out when it touches it at x equals 2, what the equation of that tangent line is. If we want to find the equation of any line, we want a y equals mx plus b. And we've talked about before that there's 2 things that we need in order to come up with that equation. We need a slope and we need a point. So we need the slope of that tangent line, or the derivative, right? And so we know from part A that our derivative at any x value was this negative 4 over x squared. So we want to figure out what the slope is at x equals 2. So what I can actually do is figure out what the derivative is when x equals 2 by plugging in a 2 into my derivative equation now. So I have negative 4 over 2 squared. Or I have negative 4 over 4, which is the same thing as negative 1. So this is actually the slope of my tangent line. That's the first thing I need. The second thing I need is a point. Well, I know that the tangent line touches at x equals 2. But that's only half of a point. I need to figure out the other half of the point where it touches. Well, if I know that it touches at x equals 2, I should be able to plug in a 2 to figure out the y value that goes with it. Now be careful, where are we going to plug the 2 in? We're not going to plug it into the derivative. I already did that. When I plug it into the derivative, I'm not getting a point, I'm getting the slope. And I already have the slope. I want to figure out the point that this tangent line touches your graph. So your graph might look something like this, and we want to know where it touches at the point. Well, if it is on the function and on the equation, and it touches at x equals 2, we should be able to plug in a 2 into my original function. Remember, my original function was this 4 over x. We should be able to find the y value by plugging in a 2 for x in that equation. So really, 4 divided by 2. 4 divided by 2 is 2, so I have a point that touches the tangent line and the graph touch at that one point at 2, 2. So I have a slope and I have a point, and now I should be able to come up with the whole entire equation for this tangent line. So when I wanted to find the slope, I plug it into the derivative, but when I want to find the point where it's at, I need to plug it into my actual original equation. A little bit tricky. All right, let's finish it up. I'm going to plug in my point and my slope into my point-slope formula. I'm going to distribute my negative 1. I'm going to add 2 to both sides, and I end up getting y equals negative 1x plus 4. That's the equation of my tangent line that touches the function 4 over x at the point 2, 2.